Hey folks, we're going to look at nuclear chemistry now. Now that we know about isotopes, we know how to name them and figure out the number of protons, neutrons, and electrons. Now we'll be able to notice any changes that happen to the protons and the neutrons. So, before we start talking about nuclear chemistry, I want to contrast nuclear reactions, nuclear changes, to other kinds of changes that you may have learned about before. For instance, a physical change. A physical change is a change in the form of a substance that does not change its identity. It doesn't change its composition. It doesn't change what it's made up of. And so some examples of this would be like cutting a piece of paper. You're not changing the substance, it's still paper. You're just changing its physical form. Boiling would be an example of a physical change. When you boil water and make steam, that steam is still water. It's just water in a gas form instead of a liquid form. If you dissolve salt in water, you still have salt and water. You're just changing the physical you're just doing a physical change. You are not chemically changing the salt or the water. A chemical change or a chemical reaction does change the identity of a substance. So you are rearranging atoms. You're not changing the atoms, you're just rearranging them. For instance, burning rocket fuel. If you burn rocket fuel, you start with hydrogen gas and you react it with oxygen gas and you produce water. I know we haven't learned how to balance equations yet, but I need to balance it. When you do this, we are just rearranging atoms. The hydrogen atoms start off stuck to each other. The oxygen atoms start off stuck to each other, chemically bonded together. But those atoms rearrange themselves so that we have hydrogen atoms chemically bonded to oxygen instead. So this example of burning is one example of a chemical change. So would rusting be an example of a chemical change. Whenever you change the identity of a substance, here I don't have hydrogen gas or oxygen gas anymore, I have liquid water instead. Nuclear changes are what we're talking about in this topic today. And nuclear change changes the nucleus of an atom. So that means, if you remember what particles are in the nucleus, it means we're either changing the number of protons or we're changing the number of neutrons in the nucleus of the atom. This is not something that we would ever do in a chemistry experiment, but we do learn about it in chemistry class. All of these changes, whether it's a physical, chemical, or nuclear change, all of these changes obey the law of conservation of mass. You cannot create mass, you cannot destroy mass. However much your starting materials weigh, your ending materials have to weigh the same amount. And that's going to come into play when we are balancing nuclear equations. So just to refresh our memory, this nuclear symbol, if you see this written down, what does it mean? First, you've got the element symbol. So if you look up U on the periodic table, it's uranium. Next, we have the atomic number. Remember, that tells you the number of protons. Uranium has 92 protons, always. And lastly, we have the mass number, which is the number of protons plus the number of neutrons. This can change between different isotopes. But this particular isotope of uranium has a mass number of 235. We need to define some particles that we're going to see in nuclear equations. The first particle you need to know about is the alpha particle. It's a helium nucleus, and so sometimes it's written with the symbol helium, with a mass of 4 and an atomic number of 2. However, we can also write it with the Greek letter alpha, again with a mass of 4 and an atomic number of 2. The second particle you need to know about is a beta particle. It is essentially an electron. And so sometimes we write an electron with a lowercase e, a mass of 0, and a proton an atomic number of -1. Now, an electron does not have protons, but it ends up kind of neutralizing a proton in nuclear reactions. So that's why it counts as having a proton count of -1. The other way to write a beta particle is using the Greek letter beta, again with a mass of 0 and an atomic number of -1. A positron is similar to an electron in mass, but it has an opposite charge. So when involved in nuclear reactions, a positron increases the number of protons found in the nucleus. So it increases the proton count, so it has a +1 atomic number, but a mass of 0, the same mass as an electron. Again, the positron, just like the beta particle, can be written with the Greek letter beta or with an E for an electron. Lastly, neutrons. Neutrons are often gained or released in a nuclear reaction, and we use these to balance our nuclear equations because neutrons don't do anything to the atomic number. They have an atomic number of 0, but they can change the mass of, they can add or remove from the mass of a nuclear equation. So how do we balance a nuclear equation? The reactants are what you find to the left of the arrow. Here are the reactants. And the products, which are to the right of the arrow, they must balance in terms of their masses and in terms of their atomic numbers. So there are kind of two things we need to balance as we are handling these nuclear equations. Reactants to the left of the arrow, products to the right of the arrow. The arrow is your big dividing line. So let's look and see why this is a balanced equation. The mass numbers on the left of the arrow have to equal the mass numbers on the right of the arrow. And on the left, we've got a mass of 235 plus a mass of 1. So altogether, that's a mass of 236. On the right side of the equation, we have 142 plus 91 plus we have 3 of these neutrons that each have a mass of 1, so 3 times 1. If you add those together, you also get 236. So our mass numbers in this equation balance. Now let's look at the atomic numbers. If we have 92 plus 0, that equals 92. And if we have 56 plus 36 plus 3 times 0, remember there are 3 neutrons here, so we need to multiply this 3 times, although 3 times 0 is 0. We also have an atomic number of 92. So this is a balanced nuclear equation because all of our mass numbers balance out and all of our atomic numbers balance out. We need to balance out the top numbers and we need to balance out the bottom numbers. So let's look at how we can complete a nuclear reaction and write a balanced nuclear equation to represent the nuclear reaction. So in this example, I start with radium and I only have radium on the left side of the equation. And then I know that I'm giving off an alpha particle here, but I don't know what other substance I have here. So what I need to do is I need to think of, remember, there's a dividing line between my reactants and my products. This 226 is 4 plus something. 4 plus something. That something is 222. 222 plus 4 is 226. You're just subtracting 4 from both sides of the equation to get your 222. Okay, so I know that my mass is of my missing component is 222. Now I need to find the missing atomic number. So I have 88 on the left side, 2 on the right side. So 88 equals 2 plus some number. Again, I can subtract 2 from both sides of the equation, and I'm going to get 86. 86 is my missing atomic number. But when I look up 86 on the periodic table, I see that I have radon. Radon is my missing element, so I type in the abbreviation for radon, Rn. Let's do another example. This one does not have an alpha particle. This time I'm releasing a beta particle from my sodium. So now we're going to be dealing with negative numbers, which sometimes students find a little challenging. Starting with the mass numbers, 24 equals 0 plus something. Well, that one's easy. 0 plus 24 is 24, so I'm going to write 24 up top. Now down below, 11 equals negative 1 plus something. Here's where you might want to use your algebra skills. Let's add 1 to both sides of the equation. That cancels out, and we are left with 12. So 12 is my missing atomic number. So 12 is my bottom number. And if I look that up on the periodic table, the atomic number of 12 corresponds to magnesium. So I write down the abbreviation Mg. And this was the missing element in my nuclear equation. Example 3, uranium, if you bombard it with a neutron, produces this iodine and some neutrons and something else. So let's figure it out. Those mass numbers, I've got, here's my dividing line, 235 plus 1 equals 139 plus 2 times 1 because I have 2 of these neutrons. If I solve for my missing number, I get 95 because I have 236 equals 141 plus my mystery number. So I subtract 141 from both sides and I get 95. So 95 is my missing mass number. Let's look down below. 92 plus 0 equals 53 plus 2 times 0. So 92 equals 53 plus my missing number. I'm going to subtract 53 from both sides of the equation, and you get 39. 39 is my missing atomic number. And if I look up 39 on my periodic table, I can see that that is yttrium. Number 39 is yttrium, so number 39 is yttrium, so I insert the symbol Y into my nuclear equation. Last example. Platinum is decaying into an alpha particle and something else. So 175 equals 4 plus something. Subtract 4 from both sides of the equation. You get 171 is your missing number up top for mass. Down below, 78 is equal to 2 plus something. Subtract 2 from both sides of the equation and you get 76 is your missing atomic number. And when you look up 76 on the periodic table, that corresponds to osmium. So you write down the symbol capital O, lowercase s. So that's how you deal with balancing nuclear equations. But you may be wondering, why are these isotopes decaying anyway? Why do some isotopes or some nuclides decay? To be stable, an atom must have a certain ideal ratio of neutrons to protons. Okay, there's a graph here that kind of shows if you have too many neutrons for the amount of protons you have, then the atom will probably go through a beta decay. Or if you have too many protons for the amount of neutrons, the atom will probably go through an electron capture or a positron emission. Or you can also have an alpha decay if you get too far with too many protons. So basically, in summary, if the ratio is too far from the ideal ratio, the nucleus is unstable and decays into different nuclei that are more stable. So let's look a little bit more. We mentioned alpha particles, we mentioned beta particles and positrons. Let's look at these particles a little bit more, the different kind of radiation that can be given off by a nuclear reaction, to look at the properties of these, because different types of radiation have different dangers. So alpha particles. If you have an alpha decay, by definition, you are producing alpha particles. And remember, we said already that an alpha particle is a helium nucleus. So we can either write it as being as a helium atom or as using the Greek letter alpha. Alpha decay happens naturally with heavy radioactive nuclei. So something like uranium in nature will decay and give off alpha particles. Alpha radiation can be blocked by something as thin as paper. It does not take much to block alpha radiation. So you may think, oh, well then alpha radiation isn't dangerous. Alpha radiation can absolutely be dangerous. It's not dangerous so long as it stays outside your body. But if you eat something that emits alpha radiation, that alpha radiation cannot escape your body, because if it's blocked by a piece of paper, it's going to be blocked by the lining of your stomach. And so all of the radiation stays inside of your body. So alpha radiation actually can be harmful if it gets into your body, less harmful outside of your body. The next kind of nuclear reaction is called a beta decay. And not surprisingly, beta decay can also be called beta emission. It produces beta particles. Beta decay produces beta particles. Remember, a beta particle, we can call it an electron, or we can write it with the Greek letter beta. But this electron isn't a normal electron that orbits around the outside of an atom. It's actually an electron that came from the nucleus. There shouldn't be any electrons in the nucleus. How did an electron come from the nucleus? Beta decay converts a neutron into a proton and an electron. Remember, a neutron has no charge. So if a neutron suddenly converts to a proton that has a positive charge, it must also produce an electron with a negative charge to kind of balance out the charges. So that's how, you don't need to know the mechanism for it or anything, but that's, I hope that you're surprised that this electron came from the nucleus. That's highly unusual. There are no electrons in the nucleus. But basically the electron appears from a neutron. In effect, with beta decay, what happens is the nucleus gains a proton, but the mass doesn't change. So here we've got thorium, and we're releasing a beta particle, and the proton number increases because of this beta emission, but the mass number does not change. So that's beta decay. Beta radiation can be blocked by aluminum foil or wood. So it takes a little bit of a thicker or stronger barrier to actually block beta radiation than it does alpha radiation. The third type of nuclear reaction or nuclear decay that you need to know about is a gamma emission. This is the Greek letter gamma, and gamma radiation is a high energy photon. Gamma radiation is a high energy photon. It doesn't have any mass, and it doesn't do anything to the atomic number. So here we have technetium with a mass of 99 and a atomic number of 43, and we end up with technetium with a mass of 99 and an atomic number of 43. We haven't changed either value, but we have released this gamma radiation. This M here basically just kind of lets us know that this is an unstable isotope and that it will decompose. This isn't something that you really need to know. I just wanted to show you a balanced equation that does have gamma radiation in it. The gamma radiation doesn't really do anything to the balanced equation. But it absolutely does do something to your body, because gamma radiation is very high energy. So you need several centimeters of lead or several feet of concrete in order to block gamma radiation. If you think about the lead apron you wear at the dentist office, that's quite thin, that's just to block X-rays, to protect your body from damaging high energy X-rays. But you need even thicker lead to block gamma radiation. One last type of nuclear reaction I just want to introduce you to. You don't really need to know the details, but positron decay or positron emission happens when a proton in the nucleus converts into a neutron and a positron. So that proton loses its positive charge, and so that positive charge has to be carried off, and it's carried off by this positron. So in effect, the nucleus loses a proton, but the mass does not change. And there are a couple of beta emission questions on your homework. There are two more kinds of nuclear reaction categories that you need to know about, and those are fusion and fission. Fusion and fission. Fusion happens when two light nuclei fuse or combine to form a heavier, more stable nucleus. And these are the nuclear reactions that are occurring in the sun and other stars. This is what fuels the sun. So we have helium undergoing a nuclear reaction with hydrogen to form a heavier version of helium and releasing a beta particle. This is extremely high energy. Obviously, this is what's powering the sun. This is why the sun gives off light and has been for billions of years and will continue to do so for billions of years. Fission, on the other hand, is splitting. A heavy nucleus is splitting into two smaller nuclei. Fission is the kind of nuclear reaction that takes place inside nuclear power plants. So what we do here is we take a heavy isotope of uranium and we bombard it with neutrons. And by bombarding it with neutrons, we temporarily make a larger unstable nucleus, which then immediately splits. And when it splits into smaller nuclei, it in turn releases more neutrons that go and hit other uranium nuclei and cause them to split. So it's this ongoing chain reaction. That chain reaction can get out of control because you see that we're producing 3 neutrons for every 1 neutron that we start with, which is why nuclear disasters are a real concern, because this process self-perpetuates. It creates the neutrons needed to start the next nuclear reaction, and it can get out of control. Again, fission reactions do produce a lot of energy, less energy than fusion, but they do produce a lot of energy. That's why we use them to fuel power plants. But fusion actually produces more energy. And scientists are looking at ways to try to do fusion in a controlled environment in the lab so that we could maybe use that as a power source. But it has not been successful yet.